Okay, hopefully now you're getting good with Lewis structures, VSEPR theory, getting familiar with the shapes of molecules and all that type of stuff. Let's go on a little bit further now and talk about valence bond theory. And now things are going to start to get a little complicated because what we are predicting about molecular shapes based on the orbitals involved turns out to give us sometimes, and most of the time actually, gives us the wrong answer to the shapes of molecules. So we're going to have to do some interesting things. We're going to have to create hybrid atomic orbitals. Let us explain what's going on here. Okay, first of all, a chemical bond forms from the overlap of two half-filled atomic orbitals. One electron in each to give two paired electrons. For example, let's look at the molecule H2S. Okay, note each hydrogen has a 1s orbital, has one electron in it. There's our 1s orbital with the one electron. The sulfur is 2s2, 2p4 with its 1, 2, 3, 4, 5, 6 electrons in it. And the question is, okay, how are we going to form a bond? Well, at this point, hopefully you can see that this sulfur needs 8 electrons around it. It has 6, but it's got this electron here and this electron here that are not paired. We can form a bond if we take this 1s orbital here and overlap it with this 3p orbital. Here's an example right here. Here's the 1s orbital for the hydrogen, the 3p orbital here for the sulfur, and now this electron will pair up with this electron. And the other hydrogen would come in down here, and here's another 3p orbital on the sulfur with its one electron, and the hydrogen's 1s orbital will overlap with it, and so the second 1s orbital of the second hydrogen overlaps with the other one, and we get this structure. And knowing what we know about p orbitals, we would expect this hydrogen-sulfur hydrogen angle, because of the way these orbitals overlap each other, to be 90 degrees. And it turns out when we study H2S, it is 90 degrees. And yay, all is good in the world, and everybody's happy, because what we know about atomic orbitals jives with what we know about the shapes of molecules. But what happens when we get to methane, CH4? Now we're going to have a bit of an issue. Because recall, when you do VSEPR theory on CH4, we find that it is tetrahedral. We've got 109.5 degree angles here. Now, how are we going to get 109.5 degree angles when we know that p orbitals are 90 degrees away from each other? They form 90 degree angles with each other. Well, first thing we need to realize is the way that bonds can form. You can only form bonds when you overlap the orbitals in this type of fashion. You can get an s orbital overlapping an s orbital like that. No problems. We call that a sigma bond. You can get an s orbital overlapping a p orbital, just head on, just like that. That is also a sigma bond. All right. You can get two p orbitals overlapping like this, where you've got this p orbital hitting head on with this p orbital. That's also a sigma orbital. Or there's another way that two p orbitals can overlap each other if they're side by side, but parallel to each other, but side by side, you can get this type of overlap. That's called a pi orbital. We're going to talk a little bit more about it later. What differentiates a sigma from a pi orbital are sigma bonds. Sigma bonding orbitals can rotate, meaning if I held this orbital constant and then spun this one around on an axis, that doesn't change the overlap. Same over here. If I took this sigma orbital here, or this orbital right here, and just rotated it like this, rotating the orbital like this, one orbital like this, while keeping this orbital over here stationary, does not change this overlap right here. But note, what would happen if I took these orbitals, held this one vertical like this, but took this one here and started to rotate it? Bad things would happen. You could see that this is overlapping up top and the bottom, but if I rotate it this way, then these two lobes are coming in and out of the paper, There's nothing, no lobes on this other orbital here for overlap, so you can't do that. So you cannot rotate pi bonds, but you can rotate these sigma bonds. Note, what if you took a p orbital like this and put an s orbital on the side of it like that? That doesn't work. That does not form a bond. Two p orbitals in this orientation, where one's here and the other is coming in this way, that is also not a bond. So these do not work for bonding. Only these types of interactions can work. So the problem is then, if you've got p orbitals that, look back up here, are 90 degrees apart from each other, where are you going to get a 109.5 degree angle? We realized, well, you can't, and so, but nature says we have to have this 109.5 degree angle, so what we did is we invented this concept called hybrid orbitals. We're going to combine the orbitals on the same atom, the s and the p orbitals on the same atom, to come up with a kind of this mixture of these orbitals. I want to go a little further than the book does to give you a sense of where these hybrid orbitals actually come from. So let us recall waves. Remember when we were looking at waves earlier, we're looking at constructive interference and destructive interference. Recall that if you have this wave here, and note if this line here represents 0, this is greater than 0, less than 0, positive, negative, a nice sine wave goes like that. And if you add the same sine wave to it, you get a sine wave with the same wavelength but higher amplitude, because this plus and this plus add together to make a larger plus, this negative and this negative add together to make a much deeper negative. Also recall what happens if you take this sine wave here and add the exact opposite to it. Well, what happens when a plus part of a wave adds to a minus part of the wave? Well, they cancel each other out. So these two waves completely out of phase with each other will cancel each other out. Constructive interference, positive parts of waves constructively react with other positive parts of waves. Destructive interference, when a positive part of a wave interacts with a negative part of a wave. And we talked all about this when we were looking at light. No problems there. Okay. We never looked at the actual mathematical formulas for the wave functions. But remember wave functions? Psi is the wave function, which is a mathematical representation of the electrons in an atom. It's just we're looking at quantum mechanics, we're looking at electrons as waves, and so the wave function is treating the electron as a wave, and this is the math that describes it. It turns out those mathematical equations have positive parts and negative parts. Note these are not charges, not positive charge or negative charge. It's just the sign of the wave function is positive, larger than 0, and sometimes in other wave functions for other orbitals, the wave function is negative. The sign of the wave function is negative. It's less than 0. But they are waves. When we look at this, we find that the s orbital, the sign of the wave function itself is always positive. There are no negative signs in the mathematical expression for the wave function of an s orbital. However, a p orbital, when we look at the mathematical expression for a p orbital, it has negative signs and positive signs. Some of the wave function has positive signs to it, some of the wave function has negative sign to it. Now we have to do a little bit of yeah, buts, and well, yeah, I want to look at this pictorially. Recall that these pictures aren't actually the wave function itself, they are psi squared, the electron density, the probability of finding the electron. So these pictures here of these orbitals are actually the square of the wave function. And for you mathematical aficionados there, you remember that take any number and square it, and it's positive. What's negative 2 squared? It's positive 4. So when you square the wave function, you actually get rid of any negative signs of the wave function. But we're going to look at, okay, I realize that I had to square the wave function to get this shape. However, before I squared it, the part of the wave function responsible for this lobe over here had a negative sign associated with it. So I am going to look at this shape and realize that the original math that describes the electron had a positive sign for this part of the wave, negative sign for that part of the wave. And let me emphasize again, these are not positive and negative charges. These are not charges. These are merely mathematical signs from the mathematical equation. Positive part of the greater than zero part and negative zero part for the math. All right. So what we're going to do, though, to form hybrid orbitals is we're going to say, okay, here's an s orbital, here's a p orbital, and they are on the same atom. Like a carbon atom has the valence electrons, the 2s and the 3 2p orbitals, all on that same carbon nucleus. So let's just look what would happen if we took an s orbital and a p orbital. And since these are wave functions, these are waves, I'm going to say, look at this. Here's my s orbital that has a positive sign to the wave function. Here's the p orbital that has a positive and negative sign to the wave function. What would happen if I added those together? Well, just like with our waves, what happens when positive wave overlaps with positive wave? You get larger positive wave. But what happens when positive wave overlaps with negative wave? Well, those two tend to cancel each other out. Due to the intricacies of the math themselves, what we find is this positive of the s orbital, the positive sine wave function of the s orbital overlapping with a positive sine wave function of the p orbital gives us a big positive sign orbital right here. And the positive and negative don't completely cancel themselves out. The positive can't completely cancel out this negative here. And so there's just a tiny little tail of negative wave function. In fact, that tail is so small, most of the time we're not even going to look at it. Most of the time we're only going to consider if this spot right here is the nucleus of the carbon atom, or of the atom, we can consider this lobe for our hybrid orbital. Okay, so we started with two atomic orbitals, the s orbital, the p orbital, added them together since they're on the same atom, here's the nucleus right there, to get this one hybrid orbital. And since we combined an s and a p, we're going to call it an sp hybrid orbital. However, this adding of these wave functions comes from an area of math called linear algebra, and linear algebra tells us that if you start with two atomic orbitals here, you have to end up with two hybrid orbitals. We added these two together to get this one hybrid orbital. Linear algebra tells us, oh, if you added the two together to get one hybrid orbital, you must then subtract the two to get another hybrid orbital. It's just the rules of math. So, here's my two orbitals here. I took the s and added the p to it to get this. Now I need to take the s and subtract the p from it. How do we do that? Well, let's look down here. It turns out positive s plus this p, that's what we did up there, gave us this type of situation, which gave us this hybrid orbital, this sp hybrid orbital here. If I want to take this positive and subtract this wave function, this wave from it, it's actually subtracting is the same as adding the negative. So I'm going to take this s orbital here, here's my s orbital, and I'm going to add the negative of this. Well, what's the negative of positive? Negative. What's the negative of negative? Positive. So basically I multiplied this orbital by -1. And the positive turned negative, the negative turned positive. So I'm actually adding this positive to the inverse, the negative of this original orbital. And you'll see that, okay, this positive now overlaps with the positive lobe on the right side. It was on the left side over here. And destructive interference between these two, we get a very similar looking orbital to the one we had up here. However, it's going in the other direction. So, when we then look at the two sp hybrid orbitals together, here's our first sp hybrid orbital. It looked like this. Here's our second sp hybrid orbital. Recall we had to have two of them because we started with an s and a p. That's two orbitals. We got our two sp hybrids, and if we put them together on the same nucleus, here would be the nucleus of the atom. Here is one sp orbital going this direction, the other sp orbital is going the other direction. Note, for clarity, I did not include the tiny little negative parts because they don't really matter. And note, they're going opposite directions. They are 180 degrees apart. But more importantly, both have the same energy. This sp hybrid and this sp hybrid have the exact same energy. Cool. All right. I'll let you digest that a little bit. I'm going to stop the video, and then we're going to go back to CH4 to see what happens there.